alright. So, let us do some simple examples. So, true first order system. What is the phase margin? What is the angle of the loop gain function? What is the phase lag of the loop gain function at the unity gain frequency if we had a true first order system? 90 degrees. So, how much margin do we have for the loop to become unstable? We can add 90 more degrees before the loop becomes unstable. So, this phase margin is for a first order system is 90 degrees. Okay. Then let us say second example. So, let us say we have A naught cube f by 1 plus s by omega naught whole cube 1 plus s by omega d, right. So, what is omega u? Assuming that the unity gain frequency is much smaller than omega naught, omega u is A naught cube f omega d. So, the phase margin therefore is nothing but (180 degrees) minus the angle of the loop gain, the angle of the loop gain at j omega u. And what is the phase lag of the loop gain at the unity gain frequency? Yeah, so there are basically two components. Due to the dominant pole, what is the phase lag? Due to the dominant pole, what is the phase lag? 90 degrees, right, that is due to the dominant pole. The minus 3 tan inverse, actually I shouldn't have, since we are doing everything in radians, then we should do this also in radians, minus 3 tan inverse omega u over omega naught, or 3 tan inverse plus actually, right, that is the phase lag. So, what is the phase margin? Is pi by 2 minus 3 tan inverse omega u over omega naught. Okay. All right. So, so now let me ask you this question. So, phi pm for omega d2 versus phi phase margin for omega d1, which is greater, which has got which choice of dominant pole frequency, omega d1, omega d2, which of them has got a larger phase margin? Omega d2, all right, and phase margin omega d3 and phase margin omega d1, which of them has got a larger phase margin? Omega d1 has got a larger phase margin than, choosing omega d1 results in a larger phase margin than omega d3. But so basically larger phase margin is equivalent to saying better approximation to a true first order system, which is also, but what are you paying when you get a better approximation to a true first order system? Pardon? Yeah. So, basically means smaller band. unity gain bandwidth of the loop gain, which is equivalent to lower closed loop 3 dB band. Okay. So, as you can see, like everything in life, there is a trade-off. If you want a better phase margin, you basically lose bandwidth, right. If you want higher bandwidth, then you have poorer phase margin. If you have poor phase margin, what does it actually mean? Yeah. So, the smaller the phase margin, the closer the system is to instability, and as you can see, for a true first order system, the phase margin is 90 degrees, and as the phase margin keeps reducing, you will the system's poles basically essentially come closer and closer to the j omega axis, and if the phase margin is 0, the there are two poles on the j omega axis. So, as the phase margin becomes smaller and smaller, what comment can the poles are getting closer to the imaginary axis, and what comment can we make about the transient response if you have two poles which are very close to the imaginary axis? Yeah. So, if you have two poles which are very close to the j omega axis, what comment can we make about the pole, the transient response? There will be a lot of ringing, because the quality factor of the poles is going to be very, very high. Okay. So, now the obvious question is, what phase margin should we design a system for, right. So, one thing is to say, well, I want 90 degree phase margin, okay, then what should you do? No, you have a high order system. You can't wish it away and say, I want this to become a first order system, correct. But if you want a very high phase margin close to 90 degrees, what will you do? The only control you have is on the dominant pole frequency. What will you do to get a large phase margin? If I choose my omega d to be super small, then the phase margin will be close to 90 degrees. But as a consequence, I now have a really small bandwidth, correct. On the other hand, if I say I want large bandwidth, then I have to keep reducing the phase margin. So, how small a phase margin you can have is basically is an engineering choice you make. So, typically people choose some people are very comfortable with so a good choice, I would say, is basically I would say maybe 45 degrees, right. There is nothing holy, it is just a choice I make, right. Some people who are very conservative will say 60 degrees, I need 60 degrees of phase margin, right. Some people will say, oh well, 60 degrees is is too much phase margin, I am losing out on a lot of bandwidth, I will push my phase margin to 45 degrees, okay. And what do you call then somebody else will come and say 45 degrees is just too much phase margin, I am happy with 30 degree phase margin, right. And then you will get even more bandwidth, but the response will start ringing even, okay. All right. So, now let us put all the stuff that we have learnt in some examples. Remember, when we had a second order system, the loop gain function was a naught square f by 1 plus s by omega naught the whole square, correct. And what was the closed loop Q? A naught root f by 2, okay. So, basically this is telling us that, well, even though the closed loop system is stable, the quality factor of the closed loop system is a naught root f by 2, okay. And that is that is not that is not very large. I mean that is very large, and therefore, there will be a lot of ringing. So, then we said okay, I mean then what did we say? Well, if you make a high order system look like a first order system, then we will have, you know, it will, the closed loop system will behave like a first order system, right. So, what did we say? We are going to introduce a dominant pole. So, rather than introducing a new pole which is much lower, it is actually easier to take one of the poles which are already existing and make it much much smaller. So, basically say the compensated system is A naught square f times 1 plus s over omega d over 1 plus s over omega naught. So, where one of the poles has been made deliberately lower, and in circuits that is easily done because you know the poles are all coming because of some parasitic capacitance somewhere. You can take a big capacitor, intentional capacitor, and put it in parallel with one of the existing parasitic capacitances, and therefore, one of those poles can become dominant, right. Now, so if you look at the Bode-plot now, what will it look like? Well, if we have to choose the unity gain frequency, right. So, this A naught square f times omega d must be much smaller than omega naught. This is omega d. Okay. All right. So, if so for example, if omega naught or omega d is chosen such that it is say omega naught by 10,000, okay, and A naught square f is say 1000. Okay. So, what comment can you make if we had the uncompensated system, what would the Q of the closed loop system be? Square root of 1000 is about 33 or something, that by 2, right. So, we will have a closed loop Q of 15 if we did not compensate the system. What should we expect now? We should be expecting to do much better because this now behaves like a first order system, right. So, what is the phase margin? Is 90 degrees minus tan inverse what is the unity gain frequency in relation to omega naught? It is A naught square f omega d by omega naught, which is nothing but pi over 2 minus tan inverse A naught square f omega d is what? A naught square f omega d is omega naught over 10,000 times omega naught, which is pi over 2 minus tan inverse A naught square f is 1000 okay, and tan inverse 0.1 is roughly 0.1, that is you know, and 0.1 radians. 0.1 radians is how many degrees? How much? Something like 6 degrees, right. So, the phase margin is not 90 degrees, right. It is smaller by some 6 degrees or so. okay. And this is right. So, basically in this case the closed loop bandwidth, so the phase margin is about 84 degrees, okay. And what is the unity gain bandwidth of or the 3 dB bandwidth of the closed loop system in terms of omega naught? What is it? Or in terms of omega d, what is the 3 what is the, it is omega naught by 10, correct, okay. Now, if the dominant pole was made 2 times larger, right, what would we say about the you will simply look at it and tell me quickly what the phase margin will be. So, it is pi by 2 minus tan inverse 0.2. So, that will become another 6 degrees smaller approximately. So, that the phase margin is now smaller than what it was before. But what comment can we make about the 3 dB bandwidth of the closed loop system? Omega d has increased by a factor of 2. So, the 3 dB bandwidth will become twice as large, right, and but then you see that you have paid for 6 degrees in phase margin, you have paid the price of halving the bandwidth.